Hello everyone, welcome to the third lesson in our series, Waves in the Real World. In the previous lesson, you discovered how to use Huygens' principle to predict the shape and position of wave fronts, and to work out the effects of diffraction on wave fronts. You also learned how to predict the spacing in a diffraction pattern for laser light that has been shone through a narrow slit. In this lesson, you will explore the interference pattern that takes place when light passes through two slits that are very near to each other. You will also explore the interference patterns formed by diffraction gratings, which consist of a large number of closely spaced slits. By the end of this lesson, you should be able to recall your knowledge of single slit diffraction, apply your knowledge to explain interference patterns formed by two slits and by diffraction gratings, describe how diffraction gratings are used, and draw interference patterns for water waves. In the previous lesson of our series, we discovered that light that is shone through a narrow slit will produce a diffraction pattern on a screen. You also learned how to predict the spacing of this pattern. In your task, you were asked to predict the difference between a diffraction pattern formed by blue light and one that is formed by red light. You should have found that the spacing of the blue light pattern is narrower because the wavelength of blue light is shorter than the wavelength of red light. Let's look at the reason for this. When we calculate the angle that the first dark fringe makes with the horizontal line, you will recall that the equation that we use is θ1 equals lambda divided by A. This equation shows that the angle is proportional to the wavelength. So, the smaller the wavelength, the smaller the angle to the first dark fringe of the pattern. This same reasoning applies to all parts of the pattern. In other words, the angle to any part of the blue pattern will be smaller than the angle to the corresponding part of the red pattern. We can therefore conclude that the smaller the wavelength, the narrower the diffraction pattern will be. Now in this lesson, we are going to investigate the pattern that is formed when laser light falls onto two narrow slits that are very near to each other. We will first use what we know about waves to make a prediction about what we expect to see, and then go to the lab to see if our prediction is correct. Remember that when the width of a slit is narrow, the diffraction pattern observed is very similar to a single source. So we can think of very narrow slits as sources of waves. Let's represent the wave arriving at the two slits using a diagram. Each of these slits will act as a source of waves. These waves are diffracted as they pass through the slit and spread outward from the slit. The waves from the two slits will interfere with each other. When they fall onto a screen, there will be some areas where the waves are in phase with each other. In other words, their crests will coincide exactly with one another, and so will their troughs. At these places, there will be constructive interference, and we will see a bright patch on the screen. There will also be other areas on the screen where the waves are out of phase with each other. In other words, the crest of one wave will coincide exactly with the trough of the other. Here, there will be destructive interference, and we will see a dark patch on the screen. So we should see an evenly spaced interference pattern of bright and dark regions on the screen. Now, let's look at some experimental footage from a laser lab to make sure that our predictions are correct. Yes, we can clearly see the interference pattern that is created when a red laser beam is shone through two slits. Can you see the regular spacing of this pattern? We can also see interference patterns with water waves. Let's visit Teboho in the lab to investigate this.
Hi guys, I have the ripple tank set up and ready. Have a look. Here we have two connected vibrating spheres that are placed on the surface of the water near to each other. It is important that they vibrate at the same rate as each other and are in phase with each other. These are called coherent wave sources and produce two sets of circular waves that have the same frequency and wavelength. These circular waves interfere with each other as they radiate outwards. Have a careful look at the patterns the areas of constructive and destructive interference form in the ripple tank. Can you see these regions where the ripples seem to have flattened out? These are the regions where destructive interference has happened, and so the waves have cancelled each other out. Notice that the destructive interference happens along evenly spaced out straight lines that radiate outwards from the sources. So this interference pattern is very regularly spaced, just as we found for our interference pattern for laser light. In between these regions of destructive interference, there are regions where the light and dark shadings of the ripples is very clear. These are regions where constructive interference has happened, and so the waves have added together at these positions. This constructive interference also takes place along regularly spaced straight lines that radiate outwards from the source. We can draw lines on the diagram to show the regions of constructive interference. These lines are called nodal lines. Well, I hope you found that interesting. Back to you, Diasha.
That was very interesting, wasn't it? Up to now, we have just looked at two wave sources that give rise to interference patterns. An interesting extension of this is to look at a long line of wave sources. This diagram shows a wave approaching a series of closely spaced slits, which each become sources for waves which radiate outward from the slits. In a similar way to what we have already seen, the waves from the different sources interfere with each other, creating patterns with bright patches where there has been constructive interference and dark patches where there has been destructive interference. Scientists have developed an instrument called a diffraction grating to demonstrate what happens when light passes through a series of closely spaced slits. These diffraction gratings have between 100 and 600 slits per millimeter. Here you can see an example of an interference pattern for red laser light that is shone through a diffraction grating. The main difference that we see in the interference pattern formed with a diffraction grating compared with a double slit is that the light pattern is much more defined and clearer. When torchlight is shone through the diffraction grating, the light is spread out into its different color components. This is because the various colors have different wavelengths, and so they are diffracted by different amounts. You will be able to see a similar effect if you allow light to fall onto a CD or DVD. Because the tracks are very closely spaced, the surface acts in a similar way to a diffraction grating, except that here the light is reflected off the tracks rather than passing through narrow gaps. Remember from your task at the end of the previous lesson that you discovered that the diffraction pattern for blue light is narrower than for red light because it has a shorter wavelength. Blue light is therefore always on the inside of the color spectrum of the diffraction pattern and the red light on the outside. So one of the important things that a diffraction grating does is to separate light into its different color components. This picture shows how a diffraction grating separates purple light into the different bands of its red and blue components. This is very useful because scientists can use this to analyze important information that is held in light rays. For example, when an electric current is passed through hydrogen gas, the gas gives off light. When this light is examined through a diffraction grating or a spectrometer that sometimes uses a prism to diffract the light, we see very clear thin lines which are called spectral lines. The spectral lines seen here are the unique signature of hydrogen. Each element has its own unique signature of spectral lines. So, by looking at light given off by various gases, scientists can tell exactly which chemical elements are in the gas. This method has been very useful in astronomy. You know that stars are huge balls of burning gases. Scientists have been able to work out exactly which chemical components make up different stars by examining the light given off by each star using a diffraction grating. Diffraction gratings are also used for making holographic images. These are images which appear to be three-dimensional when we look at them from different angles. Now, for your task today, let's recall the interference pattern that is formed by two coherent sources of water waves. Your task is to represent these three-dimensional water waves using a diagram where you show the wave fronts from each source radiating outwards. You will need to do a careful construction so that the wavelength of the waves is the same between the different wave fronts. Then, on your diagram, try to identify the nodal lines, which show us the regions of constructive interference. Also try to identify the lines that show where destructive interference will take place. So, to summarize your task, you will represent three-dimensional water waves formed by two coherent sources on a diagram. Show the wavefronts radiating outwards. Make sure that the wavelength is consistent between the wavefronts. Identify the nodal lines which show constructive interference and identify the lines showing destructive interference. Thank you for joining me today. In our next lesson, you will learn why a sound like a train whistle changes as it moves past you.